All right, so here we go. This is section 5.4, indefinite integrals and net change theorem. So in this section, we're going to take a look at what we mean when we say indefinite integrals, and we'll take a look at something called the net change theorem, which I think is one of the more important theorems at the end of the semester here. All right, so first off, an indefinite integral. Well, basically what this comes from is it comes from the parts of the fundamental theorem of calculus. We had part 1 of the fundamental theorem of calculus and part 2 of the fundamental theorem of calculus. Part 1 told us about the relationship between a function and its antiderivative. That is, we could have a function, we can have an antiderivative for that function, and we can talk about what's happening between those two. Okay? Or we can talk about what this notation here means. Okay? Now, don't worry about part 2, worry about that later. But part 1 basically leads us to this idea of, hey, let's come up with an operator, a symbol, a notation that's going to tell us to take the antiderivative. Okay? And so what it leads us to is it leads us to this right here, where if we use an integral symbol and we do not put limits of integration on it, that is, we don't put a lower limit of integration or an upper limit of integration on it, what we're basically saying is we're asking the reader to find the antiderivative and antiderivative of f. But more importantly, this notation implies find the most general antiderivative, which basically just means find an antiderivative and put a plus c on the end, which is this right here. Okay? All right, so a piece of note to take into consideration. Operators go away when you perform the operation. 3 plus 4 is 7. Where'd the addition symbol go? Oh, I performed the operation. I don't write it anymore. 24 divided by 6, that's 4. Where'd the division symbol go? When you perform the operation, you remove the operator symbol. I don't need this hanging around anymore because I did the division. I don't need this hanging around anymore because I did the addition. What is the square root of 25? Well, the square root of 25 is 5. Well, where did the square root symbol go? It's an operator. It tells you what to do. When you do it, it goes away. Same thing's going to happen here. On this left-hand side, I've got an operator. I have an integral symbol with no limits of integration, or an indefinite integral symbol, and a dx. The purpose of the dx, the operator dx, is to tell us what our independent variable is. And when I perform that operation, when I find that antiderivative, I do not write the integral symbol anymore. It's gone because I did the operation. Please don't continue to write it. It's incorrect to continue to write it. Okay? So what you want to do, what you want to take away from this is this idea right here, is that you should be able to, as an acute or an accurate viewer of calculus, to differentiate between whether they're asking you for a definite integral or an indefinite integral, and what that means in terms of your final answer. If you have limits of integration that are numeric, numbers there and there, then when you find that antiderivative, when you perform that mathematics, right, that answer is going to be a numerical value because those things will tell you to evaluate and get a numerical response. When you do not have limits of integration, your final answer is going to be a function because you don't have anything to evaluate, right? So when I do this right here, I know that my final answer is going to be a number because I have limits of integration, and that's going to transfer into my final answer being a numerical value. More specifically, it's going to be f of b minus f of a, where this capital letter F here is going to represent an antiderivative of the integrand in our original expression. Right? And so what this allows us to do is it allows us to take that table of antiderivatives and rewrite it as a table of indefinite integrals. I want you to pay very close attention. Look here and here. Do you notice how in neither of those two examples the integral symbol goes away? That's because we did not do the integration. We did not find the antiderivative. But in this example, that example, this one, 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 and this one, when you find the antiderivative, what happens to the integral symbol? It goes away. And why do they all have plus c's on them? Because the integral symbol, the indefinite integral symbol, tells us to find the most general antiderivative at every step along the way. And since our job is to find the most general, plus c on the end. Okay? All right, so here's our first example. This is example number 1. Find the general antiderivative, indefinite integral, antiderivative, for this integrand. I see 2 terms in my integrand, which means I'm going to rip this thing apart and think of this, in my mind at least, as 2 indefinite integrals. One will be 10x to the 4th dx, and the other will be the integral of 2 secant squared x dx. Okay, working the first one first. Right? The antiderivative is going to be x to the 5th over 5 minus 2. Antiderivative of secant squared is what? Tangent x, and of course a big old fat plus c on the end because we're in an indefinite integral. I'll run back through the expression one last time, cleaning up any arithmetic I can. 10 divided by 5 is 2. That gives me 2x to the 5th minus 2 tangent x, and of course on the end we have our plus c. So 2x to the 5th minus 2 tangent x plus c, indefinite integral. Same directions here. I'm looking at this with my critical calculus eye, and I'm seeing an indefinite integral, a defined variable, cosine over sine squared. I don't know that one, so I'm going to rewrite it and see what I can do, because whenever I have trig that I don't like, I try rewriting it. So it looks like that, if I write out sine squared, that looks like the reciprocal of tangent. So it looks like I could think of this as the integral of, what's the reciprocal? Cotangent, that's right. Cotangent theta, and then 1 over sine is what? Cosecant theta d theta. So I rewrote the integral to see if that rings any bells. And I think that does. Isn't there an integral for cosecant cotangent? Okay. I should know all these. I should have these memorized, but in case I don't, I can always go back up and look. And cosecant cotangent is negative cosecant, in that case it's x, in our case it'd be negative cosecant theta, and of course I put a plus c on it because I'm looking for the most general antiderivative. Right? What about this guy? This one is incredibly different than the last two, because look what's sitting right here and here. We have limits of integration, and limits of integration tell me that when I find my antiderivative, I'm not done. This is not an indefinite integral, this is a definite integral, which means my final answer is going to be a numerical value. So the first thing I have to do, though, is I have to find the antiderivative of that. Right? So my antiderivative of x cubed is going to be x to the 4th over 4 minus 6 times x squared over 2. And then this whole thing needs to be evaluated from 0 to 3. Now before I evaluate, I will go through and clean it up. I've got x to the 4th over 4 minus 3x squared evaluated from 0 to 3. Okay? I'll evaluate at the upper limit. That's going to give me 3 to the 4th over 4 minus 3 times 3 squared. And then I'll subtract off the lower limit. 0 to the 4th over 4 minus 3 times 0 squared. Right? That second term is just going to be minus 0, no worries there. 3 to the 4th is what? 81. So I have 81 over 4 minus 27 minus 0. 81 over 4 minus 27 is going to give me 81 over 4 minus 27, written as 4, so it would be 80, what is that, 108 over 4? 54, yeah, 108. 81 less 54, what's that going to be, 27, so negative 27 fourths. And so the numerical value for this is negative 27 fourths. If I'm searching for meaning, I'm not sure what it means, but I do know this. Since the final answer is negative, that original graph, if I were to take a look at that picture, on the interval from 0 to 3, there's more below the x-axis than there is above the x-axis. Okay. Same problem here. What am I supposed to do? I'm supposed to find an antiderivative because I got an integral symbol. I have limits of integration, so I know that my final answer is going to be numeric. So I'm doing a definite integral. There are 3 terms. I'm worried about that last one, x squared over 1. I can work the first couple pretty easily. Antiderivative of the first term is going to be 2 times x to the 4th over 4 minus 6 times x squared over 2 plus 3 times, what's the antiderivative of 1 over x squared plus 1? Gosh, I wish I had these memorized. I didn't have to keep scrolling back up every single time to recognize that that's arctangent. Man, but okay. Arctangent of x, and then all of this needs to be evaluated from 0 to 2. Okay? I'm going to go through and clean up before I do that. Let's see, that's going to give me x to the 4th over 2 minus 3x squared plus 3 arctangent x, all evaluated from 0 to 2. I'll evaluate at the upper limit first. That's going to give me 2 to the 4th over 2 minus 3 times 2 squared plus 3 times the arctangent of 2. And then we need to subtract off the entire thing evaluated at 0. So that's going to give me 0 to the 4th over 2 minus 3 times 0 squared plus 3 arctangent of 0. Okay? Now I know at least one person sitting out there going, but 0, but 0, but 0, but 0 always means 0. 0 doesn't always mean that the function will evaluate out to 0, especially if there's weird stuff involved like trig or logs or exponentials. So be careful with that. All right, so then working from left to right, 2 to the 4th divided by 2 is 8, minus 2 squared minus 12, plus 3 arctangent 2, minus, that's 0, but minus 3 arctangent 0. Right? Keep moving here. 8 minus 12 is negative 4 plus 3. And now can I evaluate the arctangent? The arctangent of 2. Arctangent of 2. Arctangent of 2. Can you think of an angle that gives you 2 when you take the tangent? I can't think of one. I think that's just going to be a horrible number. So I'm just going to leave it as the arctangent of 2 unless the problem asks me for an exact or an approximate value. Then I would throw it in my calculator because as it sits, arctangent of 2 is the exact answer. All right, minus 3 times arctangent of 0. Well, can you think of an angle that when you take its tangent you get 0? I can. It's 0. So arctangent of 0 is 0, so that just goes away. And so it looks like my final answer is negative 4 plus 3 arctangent 2. Let's see. That looks like a numerical value. I don't know what it's worth, so I'm going to put it in my calculator and get a decimal approximation. So let's see. Negative 4 plus 3 arctangent of 2. Make sure my mode is in, radians. I got negative 0.67 approximately. And so that tells me that if I were to graph that original function, the original integrand, on the interval 0 to 2, it looks like there's more area below than above, but not much. Negative 0.67 is approximately 2/3, so negative 2/3 of a unit below. Okay? Doesn't mean that it's all below, it just means there's more below than above. And how much more below? About 2/3 of a unit. Okay? Hey, moving right along, got another one here. We're already up to about 15 minutes for this video, so I'm going to stop it here and I'll do this next one and then we'll come back for the rest. Right? Again, we're given a definite integral, right? But I got a messed up integrand. Look at that hot mess of an integrand. 2t squared plus t squared times root t minus 1 over t squared dt. I don't know what to do with that, but I recognize something that I've seen before. My denominator is a monomial. And whenever my denominator is a monomial, what that means is I can then rip this thing apart, clean up each fraction, and hope that helps. So let's take a look. This could be thought of as the integral from 0 to 9 of 2t squared over t squared plus t squared root t over t squared minus 1 over t squared dt. You'll notice that the integral symbol is still there because I have not taken an antiderivative. That does not go away until I take an antiderivative. Please don't get sloppy and remove those things when they're not supposed to, when they're be removed yet. Right. So then this turns into the integral from 0 to 9 of 2 plus root t minus t to the negative 2 dt. Just simplifying each term of the expression. Right? Now I'll find antiderivatives. The antiderivative of 2 is 2t. I'm thinking of this as t to the 1/2, so the antiderivative is going to be 2/3 t to the 3/2, right? Plus 1 times t to the negative 1. And this all gets evaluated from 0 to 9. Right? Remember, for this term and this term, add 1 to the old exponent and then take the reciprocal and multiply. So 1/2 plus 1 is 3/2. Reciprocal is 2/3 there in front. Negative 1 plus 1 is, negative 2 here. Plus 1 gives me my negative 1 exponent there, and then take the reciprocal of negative 1, that's still negative 1, multiply it out in front, back to positive 1. Now I got to work through and evaluate this for 9 and for 0. I'll do the upper limit first, of course. That's going to give me 2 times 9 plus 2/3 times 9 to the 3/2 plus 1 over 9 minus, let's see, the second term is going to give me this. Let's see, okay, what do I do here? I go 2 times 0 plus 2/3 times 0 to the 3/2 plus 1 over 0. And at this point right here, I am incredibly, incredibly, incredibly unhappy. Can I do that? So this means that I've either done something wrong in my integration or my original problem is wrong. So I'm going to go back up here to the original problem and take a look at this. Oh my gosh, I should have recognized this at the beginning. But I didn't because I wasn't paying attention, because I just want to do the math because I'm so excited. Right? Look right here. The rule for the fundamental theorem of calculus part 2 states that the only time that you can perform an integration by finding an antiderivative and evaluating this is if your entire integrand is continuous on the interval from a to b. Remember, the lower limit is a, the upper limit is the b in that definition. And so we have a function here, an integrand here, that is not continuous on that interval. So I should have just looked at the original problem and said, no, I can't do this. But I missed that. And so I worked through the problem and mistakenly tried to do something I couldn't do. Now, luckily for me, the math showed up at the end. That's not always the case. Here's what I mean by that. The integral from negative 1 to positive 1 of 1 over x dx cannot be done. But we'll make it x squared. That makes it better. Right? I can't do that because if you think about the graph looks like this. Right? There's a hole in the middle of there. It is undefined at x equals 0. It has a vertical asymptote. However you want to say that. There's an issue. I can't do it. There's a hole in the domain. The domain doesn't exist at 0. Right? So it's not good on the interval from negative 1 to positive 1. So I shouldn't be able to do it. But if I attempt to work this out, right, I would first say, well, this is the integral from negative 1 to positive 1 of x to the negative 2 dx. So then that's going to be, let's see, add 1 to the exponent gives me a negative 1. So negative 1 times that, evaluated from negative 1 to 1. So that's what, negative 1 over 1 minus a negative 1 over a negative 1. So that's negative 1 minus 1, that's negative 2. So it looks like it gives me an answer, but it really shouldn't give me an answer because the original integrand was not continuous over the entire interval. Okay? So I need to be careful when I'm doing my math here that I don't just get so excited about the math that I forget to check to see whether I should be doing the math or not. I shouldn't have been even trying to work this problem right here because it doesn't. It's not continuous on the interval 0 to 9. It has a discontinuity of 0. So all this work I did here, this was all just wasted because it shouldn't have been done in the first place. Keep that in mind when you're working these problems. Take 10 seconds and check and go, can I do this? Before you just jump in and start doing it. Okay? We'll come back in the next video and we'll take a look at the applications of the rate of change or the integral of a rate of change, which is going to give us a total change there.